Good morning. How are you guys feeling? Energetic, lab day. One of the best. I look forward to this week in Chicago every year. I think it's a wonderful meeting. There's a lot of innovation. Full Arch Masters tries, and I try to be on the cusp of new things that come out into the market. We try to be kind of listening and interpreting what is in the marketplace. And every single year I come here, there are more, there are more and more options in our menu for full arch implant dentistry. And this year, I think especially, I got bombarded with ads on my phone as soon as I landed at O'Hare for full arch systems that replace photogrammetry or as good as photogrammetry. And all of a sudden, photogrammetry is like a has-been technology. And so it makes me laugh because, things are cyclical, right? My kids are wearing shoes that I wore when in the 80s, and they think it's new. And so I have to remind them, my generation invented that word, or my generation wore those shoes, and they don't believe me. And the same thing happens in dentistry. There's this like cyclical push and pull in full arch dentistry, especially between different types of digital methodologies. And for some reason, photogrammetry, this word, photogrammetry, it strikes a chord with people, and they get agitated and upset, and they don't want to think that they have to rely on this expensive piece of equipment, or they don't have to invest in this. They can just use workarounds, and they can use alternative methodologies. So I'm excited to talk about this little project that we started, I don't know, maybe 6 months ago, a year ago. I just had an idea one day. I'm fortunate enough to have all of these systems different systems in my office. I have intraoral scanners. I have iCam. I started my photogrammetry journey with PIC. I have a Shining scanner. I have a Tupel scanner. I've acquired these things over years because I'm interested in them. And so I thought, well, I've never really done a formal comparison of the actual numerical data. We talk about passive fit, we talk about reliability, predictability, but we never really had a quantitative way to analyze data. And so I contacted my friends at iMetric, and I said, I want to do a test, and I want to test these different systems for their repeatability. I want to see if there's one clear winner for my education purposes and also for my clinic. And so I contacted them. I said, I'll acquire the data, but I'm not a mathematician. I'm not an engineer. I need your help. Let's come up with a way to make this easy and digestible for myself, where we can actually look at these two data sets. So that's what we did on a day, just kind of randomly. I had a patient having surgery, and I said, let's just double scan. Let's just do a bunch of scans on this patient while she's asleep, and we'll compare the data. And so when I go through the different types of data that we got, it became very interesting to me. And as I learned more from the engineers at iMetric, some of the problems that I have seen in my practice over the last 15 years could be attributed to inaccuracies that I had intrinsic to these cases that didn't show up right away. I can fix immediate problems. They're very easy to identify. They're very easy to address. An implant fails right away, something breaks, you remake it, you're within the healing period, the patient forgives you, everything's fine, the lab works on it, it's not a big deal. Well, fast forward a year, or 2 years, or 3 years, or 5 years, 8 years on these prosthetics, and what happens when things start to go south then? Huh? Okay. Now I'm a busy clinician. I see patients 3 or 4 days a week. And I see these people longitudinally. I'm not just there for one point in time. So I see these people longitudinally, and I would see patients 5 years down the road, even 10 years down the road. And when things have gone south, and these cases are never forever, we'd love them to be, but our patients are younger, and we're doing more for these patients at an earlier stage in life. So to ask these full arch reconstructions to last 50 years we just don't know. I don't expect them to, and we just don't know, and we certainly can't guarantee that things are going to last this long. So when patients have failures or their case needs revision, who's to blame? Like, what is the culpability between the patient, between the doctor, and the laboratory, right? It's, like I said, it's very easy to justify repairing something that just occurred. I did your surgery 2 weeks ago, you have a complication, and now we're going to repair that. But what about the 5-year mark and the 7-year mark? Who's going to be to blame, and more importantly, who's going to shoulder the financial responsibility for that revision, right? The patient may look at you and said, hey, these teeth were forever. You told me that this was going to be worth it. And now here I am 5 years in, and you're telling me that if I can't afford to redo this, I'm in a denture, right? So I got very interested in what these true numerical values are for this wide array of systems that claim to be as good or replacing what I consider to be the gold standard, which is ICAM photogrammetry, right? So these are the questions that entered my mind. You know, is it my scan data? Is there an inherent inaccuracy in the data that we're acquiring with these systems? Is it my scan bodies? Was it my workflow, the lab? If you can't identify the source of the error of why things went south, you're just going to repeat the cycle. And when you practice dentistry, in my capacity, I'm not, like I said, I'm with these patients for decades, right? And I don't have the option of just waiting 5 years or 7 years to see if things work. So that's why we embarked on this journey. And I really wanted to see if the data that I was acquiring from different systems was truly reliable data. So this presentation is going to get a little mathy. So I'm sorry. I try to keep my lectures very interactive, but there's some interesting things that we'll talk about. If your data can't be repeated, then really it can't be trusted, right? So this is a very simple example. If you got on a bathroom scale 3 times and it gave you 3 different weights, you wouldn't trust that scale, right? You would throw it away, you would get a new one. You wouldn't just say, oh, well, we'll take an average and we'll hope for the best. Lowest. Huh? Right. Assume, right. So our instruments have to be precise enough to get extremely reliable and repeatable data for us to be able to trust them. So if it can't be repeated, then really it can't be trusted. Same rule applies to implant position data as it does to our bathroom scale. So if you have a data array that looks like this, if you take the average position of all of these points, it's spot on in the middle. But you know just from looking at it that there's a big deviation in all of these data points. So this would be a marksman that we cannot trust, right? But he did get a bullseye, right? So the numbers can be more misleading, and I wanted to find some sort of quantitative measure for this. Just kind of some research showing that complications in most of our full arch cases don't show up for a long time. And we kind of inherently know this. And if you're in practice or in lab, you know that once you ship that arch out or once you install that full arch case, it's not like it's just sailing off into the sunset and you'll never see this patient again. We see these patients come back and back and back, and most of our complications show up later rather than earlier. The surgical techniques are getting better, the implants are getting better, the multi-unit abutments are getting better, our data acquisition is getting better, so our immediate results are getting better and better and better. But the long-term results and the long-term complications are tied to a different set of variables. Patient care, their medical status, your occlusion, forces like cantilevers. You don't see the effects of those things within the first 3 months. You see the effects of those things at around 5 years. So full arch dentistry has been judged by its accuracy based on this ridiculous notion of passive fit, right? Who are my lab technicians in the room? Okay, mostly. Dentists? Some. Okay, so when you're on the phone with your lab or you're talking to your doctors, you ask them, did it fit passively, right? Was it a passive fit? We just use this term like it's ubiquitous. And what it really means is, did it feel secure when you screwed it down, right? Did it squeak, or did it rock, or anything like that? We just ask this kind of arbitrarily based on how well the arch fits on a model and how well the clinician feels it fit. Maybe do a Sheffield test, a one-screw test. Oh, take an X-ray. That's a good idea. If it's just sitting on the MUAs, then it's good, right? Well, extrapolating this data out, it's really not that good. We should have a better way. So they don't fail when you're looking at them on the computer or on the master model. They don't fail on the X-ray. They fail in the mouth under repeated stress. So this notion of passive fit is something that we really need to update, right? Everything is going digital, everything is going quantitative, but we haven't really established a threshold that we can measure quantitatively for these cases. So this comes up all the time. If bear with me for a moment, the argument of accuracy versus precision. So your precision, as we probably know, is your repeatability, right? How many times can you hit the same dot, right? Your accuracy is how close is that dot to the bullseye, right? So the bullseye is, in our case, the actual true placement of the implants in the mouth. Now we can't actually measure that unless we rip their mouth open and put them on an industrial size scanner and, get measurements that way. We're stuck measuring the precision of our instruments. So how well can we precisely take measurements over and over again? So accuracy is what most systems claim, but precision is what the system can produce, right? And precision is what we can measure. So you can appear accurate on an average, like these two data sets, but you can still have a dangerous variation within the two data sets, right? So this is where it gets a little mathy, and this is where I relied heavily on the engineering team at iMetric, because I said, how do other industries evaluate precision? Like, we're not alone, right? Aeronautical parts have to be so precise. Medical, neurosurgical parts have to be so precise. Like, what is the statistical analysis process for measuring accuracy and precision? And they said, well, it's this thing called 6 sigma. And I said, oh, is that like a fraternity? And they just reminded me that accuracy can never be better than a device's precision, right? So if somebody comes up to you and says, my device measures to within 30 microns, that's very accurate. And you go, wow, that's great. And then when you look at their repeated data, they're getting 80 microns of deviation between data sets. There's no possible way that that machine or device can be accurate to 30 microns. You're getting a variation of up to 50 or 80 microns between data sets. So to claim that something's accurate to 30 when even its own repeatable data is greater than that means that it's just a marketing claim, right? So we'll go through kind of basically what this 6 sigma analysis looks like so that you guys can kind of see that. So this is what I just talked about. If there's accuracy within 30 microns, we say it's good enough, it's going to pass a passive fit test, right? But to me, I don't think that we need this anymore. I think we can upgrade our threshold analysis and really be quantitative about this. This we talked about. Accuracy claims are not a guarantee of repeatability. I said that from case to case in clinical use. Just because these devices claim accuracy, we can't really measure accuracy. Accuracy is a hope and a dream. It'll exist in the patient's mouth and nowhere else. But we can measure the precision, okay? So if a system doesn't disclose the precision or the repeatability, then the stated accuracy provides no insight into the worst case scenario. So if you extrapolate out into hundreds and hundreds of arches, if the precision of the instrument is not below a certain threshold, then at greater and greater volume, you will start to see problems with fit. So if we're going to use this number of 30 microns as our threshold that we want to be below, then this statistical tool of the Six Sigma suggests that in order to stay below this 30 micron level, we have to have a data accuracy of about 5 microns, because 6x of that standard deviation is going to stay within the 30 micron threshold. So if a system claims that it's accurate to 30 microns and it's therefore passive, going to give you a yield of passive fit, if you extrapolate that data out and using a Six Sigma analysis, you're already going to be at a potential 180 micron deviation within that data set. So again, little mathy, but this is kind of the foundation. So they came to me and said, well, this is a great idea, Dr. Dunlop. We are on board with this. We want to help. And so if you give us some data out of your clinic, then we will create a software that anybody can use to evaluate the precision of their instrument. And I thought, wow, that's exactly what we need. We need a widely accessible, open to the public, online software where anybody in the country, anywhere in the world, anybody can take a repeated measurement and upload it to a website and almost instantly get a measurement report for the precision of that instrument. Then, when I get bombarded with ads on Facebook for a new precise instrument, I don't have to say, well, let's hope it's good. I can actually test it. And I can test the ones that I already have as well, okay? So that was kind of the origin story. How FitMeter works, it's a very simple software, and I think it's supposed to be available within the next couple of months, right, to everybody. The website is live. We're gonna have kind of a beta program to allow people to submit cases so that we can start building this database. And it relies on what we call the double measurement protocol. Okay, so you have a patient in the chair, you have a model in your lab, and you put the, in this case, ICAM scan bodies onto that patient or onto the model, and you take a measurement. We all know it outputs a static data set that's connected. Without changing the scan bodies, without removing them or doing anything that modifies the data set, you just take a second measurement. It takes an extra 30 seconds, right? Now we have double scan data that we can put into this software and analyze the results. So first scan, capture implant positions as you normally would. Second scan, start a new case in your software and repeat the capture without moving the scan bodies. Upload both data sets. Seems clear? Okay. The FitMeter analysis will report on the X, Y, and Z deviation, angular deviation, and overall repeatability of the system. Okay? So it's agnostic. It's not looking at something from the perspective of iMetric or from the perspective of MicronMap or from the perspective of true abutment. It's just numbers, and that's what I wanted. So you go to the website, you start a project, you put in the name, lab name, clinician name, you put in the patient's information, you select the device that you're doing, you upload a data set here, and you upload a data set there, and then you press analyze. That's about as complicated as I like things. Okay, so we kind of talked about this, the difference between precision, accuracy, and trueness. I'm not going to really go through this again because I think we understand it. We have an array, even though we did accidentally get a bullseye, great. We have a very tight array that's very close to the trueness factor or to the accuracy. And then we have a very tight array, but there's an intrinsic error built into the system that we don't know about. This we said again, accuracy can't be better than precision. So if a system claims accuracy to 30 microns, you need to ask them about their precision. And if they don't want to give you the precision numbers, it's because they don't want you to know them. So which one of these would we consider passive? They showed me this picture last week, and I said, well, just based on look, I would say that's passive. I would say that one's passive. I might say that's passive, but probably not. and then the other ones are way off. So what is this? This is their attempt, iMetric's attempt to really show what a 30 micron discrepancy looks like. This is a bar that was designed and milled by them sitting in one data set. And this is an MUA surface simulated sitting in another data set. And we wanted to see if the bar believes the implant shoulder is here and the other data set says the implant shoulder is here, what in reality does that actual fit look like, right? So now we can really see that there is daylight going through the fit, even at that passive 30 micron level, okay? Did I say that right? That's complicated. So just saying that something fits on a model, just saying that something fits in the mouth, in my opinion, having done full arch for greater than 20 years, that's not something we need to rely on anymore. So that's why I think that this software is going to really set a new standard. We talked about that. Okay, so this is just the super mathy part. I talked about this Six Sigma quality control methodology, and this is not something we invented. This is established science and math. So this is how people analyze precision and acceptability in mass manufacturing capacities. So to me, it looks like a bell curve, right? So most of my grades were in this section. A lot of my friends, their grades were up here. But this is basically an average. And then as you get further and further away from the mean, this represents 1, 2, 3, 4, 5, and 6 standard deviations away, okay? So if 1 million manufactured parts pass a 6 Sigma test, then it's a very precise manufacturing process. Does that make sense? So if something can pass a 6 Sigma analysis, then it's deemed to be a very reliable data set, okay? If you achieve a 6 Sigma all the way to the right or to the left, and you're within this confine, when you manufacture 1 million metal bars or arches, you will have only 3.4 errors intrinsic in the data that cause some sort of misfit, that don't pass this 30 micron passive fit threshold. Does that make sense? So if a data set can pass a 6 Sigma, then we can call it a very precise data set. So in order to keep our restorations below 30 microns on a consistent basis, we need to have a fit of about 5. I said that before. So 5 microns, that is like Mount Everest, right? That is super, super, super accurate. But maybe we should hold, if we want to say 30 microns is our passive fit threshold, then we have to hold these systems to this standard, okay? So when I did this analysis, I looked in my office and I said, well, right now I've got 5 systems that I can use because I have them, right? And so I was curious about what would be repeated measurements using each one of these devices on the same patient at the same exact time without changing any parameters. So that's what I did. Let's see if it plays this video.
You did 2 scans for every single device?
Yeah, I'll show you. This is AI music, by the way. If any Spanish speakers, you can listen. Don't risk it.
Hey everybody, it's Dr. Dunlop from Full Arch Masters. It's another exciting day here in Fresno, California. We're doing some live patient testing on a variety of products that are out on the market. So we're gonna use the same patient, live surgery. We're gonna be testing an entire spectrum of photogrammetry and intraoral scanning devices today. And we're gonna use our lab software to compare the accuracy of all of these different scans. So kind of a fun exercise. There's a lot of different products out there on the market, and Full Arch Masters always wants to be ahead of the game, unbiased, presenting the data for what it is. Hang out for the day and check out what we're doing, and we should be giving this wonderful patient a brand new smile very shortly.
Brillando en la
everybody. So we're done with our surgery. We removed 2 of the old implants that I had placed about 10 years ago. And then we placed 4 new implants. So you can see that she's got her ICAM flags in. This is the first test that we're doing. We're going to take a series of photogrammetry and intraoral scans today on this lower mandible to show the repeatability, the precision accuracy of these different methodologies. So we're going to do ICAM, we're going to do PIC, we're going to do micromapper, Tupel, Shining, and we're going to have data sets for all those. So it should be really fun to see.
We feel the pressure rise, fire's burning deep inside. Old winds held us back, future is ours, we're on the attack. Can't stay where we've been, comfort's pacifying sin. Good is the cage we're breaking through, success is coming for you. Every scar a metal weaver, every failure a lesson learned. We're not here just to survive, we're here to thrive. Level up. Hey, no fear, no change, no giving up. Hey, push through when it gets tough. Shoot for the sky, we'll rise above. The best never rests to rise up. Level up. Level up. Mirrors show who we used to be, but we see more than they can see. Excellence is not a place you find, it's built in sweat, heart, and mind. The worst thing is feeling fine, so we crossing that finish line. We won't settle for almost great, we'll rewrite fate before it's too late. Pressure makes a diamond shine, every moment's battle line. If we fall, we'll rise again. Let the war begin. Level up.
More bass in here.
No fear, no change, no giving up. Push through when it gets tough. Shoot for the sky, we'll rise above. The best never rests to rise up. Level up. Level up. Rise from the doubt, from the noise, from the fear. The voice of confidence is all we hear. This our fight, we are born to shine. We won't stop, this is our time. Level up. No fear, no change.
All right, so we finished up the surgery on the lower. We scanned with our Shining scanner. We scanned with our ICAM. We scanned with our micromapper. We scanned with our Tupel. We scanned with our PIC scan. So we got 10 scans total, repeat scans on each one. So this is going to be a very reliable data set in a live surgical situation where we're doing a immediate load, same day smile reconstruction for this patient. So we get repetitive data, and we're going to see what the accuracy of all these systems looks like in a live surgical field. All right, that's the theatrical release. Okay, so this is my disclaimer. So, because I see a lot of faces I recognize, I see a lot of industry leaders in here. People are very interested to see. This data is going to be made completely public, okay? And the software will be available to anybody to use. This is not going to be a closed door, biased analysis. I'm not here to present my biased opinion based on my relationship with iMetric, even though they are the sponsor for this event, right? I encourage all of you to use this software to validate and interpret results for yourself. That's my goal. The following results are simply based on the double measurements on a live patient in a controlled environment at the same time, same patient, using the same software for analysis. So I don't want you to think that I'm up here telling you that we made this happen a certain way. This is just the way that the data came back for this analysis. So yeah, we went through this kind of in depth here. So this was the complete study that we did. This was my wonderful patient Sharon, who was sleeping in that video. Her lower jaw was an immediate load, same day case. So I removed 2 old implants. I placed 4 new ones, tightened down the multi-units to manufacturer specifications, and then we took a live surgical measurement. She also has an upper arch that I did maybe 15 years ago. And so these implants are totally stable. And so we measured her upper jaw as well as kind of a heel control. And then we also decided to do a static model on the bench so that we would have a third comparative analysis outside of the mouth. And so double scans on each one of these using 5 different methodologies. Does that make sense? We talked about that. So let's look at the live surgical data. The first system that we put through this rigorous threshold where we want to try and keep our accuracy precision measurement under 5 microns so that our 6 sigma measurement is under 30 was the ICAM. And so out of the 4 spots, the 4 implant positions, we tested within this tolerance for 3 out of the 4 sites. And this one missed by half a micron. So technically it doesn't pass. Yeah.
Yeah, when you do the 2 sets of...
I was like, I know you, Arturo. Yeah.
Yes, sir. When you do the 2 sets of scans, were you switching the scan bodies?
No,
for the
not
second
moving.
set? You left them exactly.
Put them on and then leave them exactly as is. That's fundamental, because as soon as you unscrew something and retighten it, technically it's not the same data set. So all of these were done without touching the scan bodies, and that's absolutely crucial if you're going to really use this the way it's intended.
Did you check that each scan body was seated?
So on the mandible, it's open flap,
Yeah.
right?
You can see it.
So I can see it. On the upper, we took X-rays because there's theoretical tissue, and then on the model, obviously, we could see it. Yeah. But just as an aside, clinically, I always take my photogrammetry measurement or any implant measurement with an open flap. That's just that's what I teach, and that's what I do. Yeah.
Isn't the ability to see the flags in a repeatable way also inherently important to this process?
100%, and that's why we didn't move them.
No. Wouldn't you want the placement of them and repeatability of your ability to place them to also be?
Right, so that's the difference between manufacturer error and user error. So if you don't put any scan body on correctly, you're not going to have the true measurement. But if you even if it's on incorrectly, you can still measure precision if you don't remove it and put it back on. Does that make sense?
But you're more interested in accuracy for your patient.
I'm very interested in trueness. I'm very interested in accuracy, but those things are not measurable. Precision is measurable. So yes, 100%. Anything that you can do to ensure that any impression coping or scan body is seated fully, that's number 1, right? But past that, let's say you do achieve that, how reliable is the device that you're using to capture the data once you are confident that all the scan bodies are seated? So do you see how that, for me, that's a different set, that's a different responsibility. Our clinicians and lab technicians have a responsibility to make sure that they're attaching componentry correctly. That's user error. Our manufacturers have a responsibility to make devices that can yield a repeatable measurement. Those are 2 different responsibilities. So yes, everybody should make sure that scan bodies are seated. But past that this is the numerical analysis for what happens past that point. Does that answer your question?
I guess my point is more, I would encourage you to repeat this investigation, but also reseating multi-units. So if one system has a multi-unit or a scan flag or scan body that is very easy to see correctly, repeatedly,
Right.
it's going to be an inherently, assuming the optics are all equally precise, it's going to be inherently more accurate than another system, which is more difficult to seat them correctly.
Fine. So yeah, you could have a whole separate argument about centering screws and materials of the scan body and the shape of your multi-unit abutments and the screw tolerances and the sterilization protocols, and there's like a litany of things that we have to talk about in order to really have the best conversation. But to this point, at least in my career, I've never had a way to actually quantify the precision of my measurements. And for me, assuming all of that other stuff is already being talked about and being done, this is the one that I think I needed to be able to really justify and rationalize. So, yeah, I agree with you. But I think that this software is more powerful when you leave the scan bodies perfectly alone. If you unscrew them and screw them back on, you are introducing human error where there shouldn't be.
Could you test your final product with the same software? Is there a
Could you test your final product?
the passiveness from this data? Can you capture that data within your final product? Bring the original data
Right.
and the final data of your manufactured.
That is something that could be used. So what I have told iMetric is that they need to give us reverse flags that go into the prosthetic so that we can take a measurement and test compared to what the measurement that was taken in the clinic. And so I've said that for a little bit of time, and I think that that's on the horizon, and other systems have introduced that, and I think that's great.
So what would be the difference in that if you're fitting them after as opposed to receiving them and taking the extra?
Let me see if I understand your question. So what would be, can you
So
kind
you're
of,
saying put flags also inside before.
oh yeah, so we're adding on to
Make
this.
sure that they're
Right.
measuring up. So what's the difference in doing that or just fitting it and taking the x-rays and seeing the difference in the microns?
Well, you can't see the difference in the microns using any radiography.
Oh, okay.
Yeah, you can't tell what a micron level fit is going to be just by a Sheffield test. Those are kind of qualitative.
Don't you like zoom in on? Like,
Yeah, but the best resolution you can ever get on a CBCT, let's say, is about 150 microns. The best resolution you could ever get on a panoramic X-ray or a PA might be 0.5 millimeter, right? So those measurement devices, although that would be fantastic, they're not even close to precise enough. Yeah.
Were they all brand new scan flags that you used for this exercise? Like,
For my purposes, it was what I have.
it was,
Yeah.
do you think that there's any chance that a scan flag that has been used 50 times,
Yeah, it's very possible. And all of these flags were just from my regular inventory. So yeah, like I'm not standing up here saying that every research parameter ever created from the Harvard caucuses of blah, blah, blah was adhered to in this study. This is, kind of a in vivo, just an analysis to introduce a software. Yeah, so, but ideally, yes, it would be all, I guess, brand new or whatever, but I think it still holds water. Any other? Yeah.
The reverse scan bodies flags, whatever they call them, is to check the accuracy of the production.
Yes, the manufacturing.
Yeah.
Right.
Not,
Right.
yeah, so.
The ongoing argument for photogrammetry is that there is compounding error that is inherent to our manufacturing process. Our sintering, our milling, our assembly, there is a compounding domino effect of errors that grow through the manufacturing process. Our job as lab technicians, owners, dentists, is to decrease that compounding error with our workflows. The argument for photogrammetry has always been that starting with the best quality data set is going to lessen the burden of decreasing the compounding error over time, right? That's why we like it. That's why we use it. So the conversation we just had is to compare the error in your manufacturing process to the data set from which it was built. But that's kind of a separate thing. Okay, so first scan, 3 out of 4 implants were within this extremely stringent threshold of the 6 sigma 30 micron ceiling. Just so you know, if it passes that threshold, it's going to show up as green. You can look at every implant individually, and it will give you tolerances and fit for each site if you want to. If you want to look site by site in X, Y, and Z angulation. And if one shows up as a red, that means that it doesn't mean that it's not acceptable clinically. It just means that it failed the mathematical analysis for that site, that the 6 sigma is greater than 30 microns, and therefore the individual standard deviation is greater than 5 microns. So again, we're holding ourselves to the absolute highest standard, okay? Okay, using the same methodology on the same patient at the same exact time, we then used my pick system and got this similar outcome with a little bit different interpretation results, because our fit was about 10.5 microns individually, and then as a 6 sigma group with that extrapolated standard deviation, we're looking at a plus or minus 63 from the trueness, right? From the potential trueness. Next, we looked at the Tupel scanner that I have on the same case, and we found the individual deviation of 33 plus or minus, and the 6 sigma of about 200. So now we're starting to get some interesting results, right? Because the first 2 systems, even though they didn't pass this super high level of expectation, they almost did. And now we're starting to see kind of a drift in the data, right? Then we kept going. We did the Shining Elite. This is the intraoral photogrammetry system, right? That's supposed to allow you to use an intraoral scanner to capture photogrammetry data similar to the way that extraoral photogrammetry data is captured. At least that's the line. That's kind of the marketing. And so we saw a 15 micron deviation between any individual ones, and that 6 sigma threshold of about 91, or a measurement of 91. Next was our micron mapper. And again, this is just on the mandible live surgery repeat data. We saw a deviation of up to close to 60 and a combined 6 alpha. This doesn't mean that it's 348 microns off, by the way. That's not what this means. This means that between any 2 sites on the 2 data, the max deviation was 60 microns. But the extrapolated statistical analysis shows that out of 1 million tries, you could get upwards of 348 microns, right?
Are we assuming the first iMetric data was the control?
They're not controlled. So this is independent. This is controlling within itself. We're not comparing. That's why I put that disclaimer up. I'm not comparing systems to each other here. I'm comparing the system to itself, right? Huh? First scan to second scan, not comparatively within devices. This is just first scan to second scan. And then I thought, well, live surgery, implants can be moving slightly, right? Abutments might not be torqued down. There could be bone in the way. That's our hardest one. So let's do something that's a little bit more forgiving. We'll do her maxilla, where the implants have been in the mouth for years and everything is stable. So again, we started with the ICAM. We took the double measurement. We saw pretty similar results to what we found on the mandible, which is not passing completely, but getting relatively close. So 7.8 microns with a 6 sigma of close to 50. The pick was similar as well. 6 microns of deviation with the 6 sigma of 36. Tupel, similar, at least in concept, to what we saw on the lower jaw. Same with Shining Elite. And remember, this just means that one scan to the next, they're not passing this super stringent 5 micron level, which will then yield a consistent measurement of 30 microns or less. Micron mapper. And then lastly, I think it was Helen's idea, maybe someone's idea, to do a model. She had a model with her. We didn't want to do all of these implants, so we chose 6 of them. I thought that was acceptable. I don't really do cases with 8, so it didn't make sense to do all 8. And again, so this is the first time that I actually saw green. And I was like, okay, at least on a model, saliva-free environment, no movement. We could at least get one data set to pass. So that's encouraging. This was for ICAM. Pick struggled a little bit on the model compared to in the mouth. Tupel struggled as well a little bit. 25 micron deviation, 150. Shining, not terrible, got one pass. Micron mapper. Okay. And then, so this is just a repeat. This is a physical manifestation of the numerical data so that we have an illustration of what this truly looks like. So we took one of the data sets and we milled a bar in true position to data set A, and then we milled a connection in true data set B. So we could see physically what that gap looks like, potentially, okay?
Dr. Dunlop,
Yeah.
did you see any correlation between 4 implant sites and 6 implant sites with the different systems?
Well, it's measuring each site individually and passing or failing it. So it doesn't matter if you have 4 or 24. But then as a group, you can look at the combined deviation. So to me, there's no difference between 4 and 6 from a numerical standpoint. Okay, so summary of fit values for me in this instance. This is a summary of blue model, red upper, yellow lower, okay? And again, not comparing system to system. It's comparing system to itself. This is a 10 micron average, 20, 30, 40, all the way up. And so you can see some trends of increasing deviation from system to system. And this is for 3 different approaches. This is when you extrapolate and push this data through a blender and push it through that 6 sigma bell curve and say, well, if we did each one of these devices 1,000,000 times, what would the statistical threshold look like? Okay, so this just kind of pushes this data out and makes it pass or fail the six sigma tolerance test. So takeaways. Most of these devices make accuracy claims that are just a promise. They just tell you that it's going to be a certain value you can depend on. But really, that's just marketing. Until devices take the challenge and put data through the FitMeter, their claims are just going to be something that was made in thin air. The quantitative side of this will give us as lab technicians, dentists, the power to truly evaluate these devices, okay? So FitMeter verifies precision, and you can use this to test new technology. So if somebody comes to your lab, comes to your office, and says, I've got a new machine, a new device, it's gonna replace this, it's a game changer. I love that word. It's a game changer. I'm just gonna say, let's go, I have a patient in the chair, Lucy's here, or I have a model right here on my lab bench, let's test it. We're gonna take double measurements. It's free, it's accessible to everybody in this room. Go to fitmeter.io, is that the right website? Huh, for the beta, yeah. And it's gonna be totally available and ready for everybody's use. Right now, I think we're just gonna limit it to beta testing so we can make sure the website's working. Huh, 20 cases, okay. I see. And just as a side note, if you're using a device that exports The file type that iMetric does, or I think maybe there's one other system that outputs the actual numerical values, it just goes right into the software. If you're using something like an intraoral scanner or another system where it's not outputting a numerical data set, you have to take that to Exocad and make a very quick bar. You have to make like any shape, any whatever bar, so that we can link the data set together, and then you send the bar file to us, and then we use the bar file inverse data to run this analysis. So that's just as an aside. If you're using ICAM, and I think there was one other in that output the right type of numbers, but if you're not, if you want to still test it, let's say you want to test Straumann's new scan bodies with Trios, and you want to see double scan what the deviation is between those two data sets, you'll just have to extrapolate that data, take it into Exocad, make a bar of any shape to connect them, and then send the bar file, and that's how we will be able to reverse engineer the numbers that we need so that it's just a numbers analysis and not physical bias.
Do you have a theory as to why the upper struggled a little bit more with, like, across the board with all the cameras?
Yeah, good question. Let's see. So, did it though, right? So this device as a group had lower numbers, right? So blue and yellow were the lowest. This device as a group had blue higher here. So I'm not quite sure I agree. I think that within each system there was deviation, but not necessarily upper to lower to model, at least not correlative.
Really surprised for a few of them that the model sigma was
Right.
higher than the, I mean,
Right.
what do you think caused that?
Data don't lie. Yeah, I don't know. It doesn't, all I have are these numbers. So what I told them to do is open this up to the public, open it up to every lab, every clinician, and let's start building an anonymous database online where anybody can go in and say, oh, there's been 20,000 scans on iMetric, and this is an ongoing anonymized database that you can just click on and see what everyone else has submitted, right? So you don't necessarily have the burden all on yourself. It's kind of a communal project, right? So what I want to see is on their homepage, it just says, here's all the systems and all the data that has been submitted and tested thus far. Use it for yourself, make decisions based upon other people's data, or get your own. Submit your own files and go from there.
Question. So on all the different ones, all the software was updated. It was all the.
It was just me at a point in time.
Okay.
Yeah. So I think he asked this question before. Were they new scan bodies? Were they seated all the way? What's your sterilization protocol? All of that stuff matters. But for this analysis, and this is how it's going to be for everybody doing this, they're just going to take a snapshot at their point in time, repeat scans. That's all that I asked. Because once you start getting into analysis of data and this and that, you can make the argument that, well, maybe I didn't screw down one of the pick flags all the way, but that doesn't affect this test. This test is just repeated measurements at one point in time where the scan bodies didn't move.
Tested digital photogrammetry against the old analog because my dentist was very against digital, and I kind of brought it there. And
He sounds great.
no, he's wonderful. He's not here. I can talk about him.
Yeah.
But I will say, a lot of times the photogrammetry ones fit perfectly and very passive, where the other, but it's like they're two totally different.
Right. Well, I mean, we're here talking about digital versus digital versus digital. If you want to talk digital versus analog, let's go grab a beer and we'll talk some shit. But we're here as the apex of the pyramid, right? We're here saying, no, 5 microns is what it has to be. Like we're the tip of the spear, right? So if you're going to make the argument of digital versus analog, like till you're blue in the face, this is pushing systems to back up the claims that they make that they use to sell product, right? We are the consumers. I am a consumer. You are a consumer. When you go walk that floor, they are all here to sell stuff, right? I'm here to give you a tool that you can say, I would like to put your device through this challenge. You guys have a model? Oh, it's sitting right there. Let's take 2 measurements. Oh, there's a laptop. Let's upload this data right now. That's my goal. So that systems that are coming to the market and making claims, we have more power in our pockets as the clinicians and as the lab to be able to discern through the weeds and get to the numbers. Are you going to say preach?
So what happens in a clinical setting when they fail? Like, what do you do?
Right. So that in my disclaimer, I said, do what you want with this. This is just a litmus test. In my hands, I'm a clinician, I'm a lab owner, so I make my own prosthetics. We make prosthetics for lots of doctors around the country. I want to know that I'm starting with the most precise data set for them because I know that there's going to be intrinsic manufacturing errors. So if I have data coming in from an outside doc that's using the new, scan body system from Dr. So-and-so from Belgium, I'm going to say, well, hey, can you take a repeat measurement for me and let's run it through this free software to make sure that the system you're using is something I, as the lab manufacturer, can depend on. And if it's not, if I get all reds, I'm going to want to send a verification. I'm going to say, I know you want me to make this zirconia, but I need to send a milled bar. I want you to try this in because your device, it doesn't give me repeatable data, and I don't want to warranty and go through the process and this and then have a prosthetic that doesn't fit day one or worse, causes problems down the road.
So you're saying as a lab, you're not gonna warranty systems that don't pass the?
I think that's aggressive. I wouldn't do that, but I would want to verify before I create that warranted product, right? So if somebody sends me photogrammetry scans right now, and they say these were taken at surgery, and now we want to make a final prosthetic off of it, most of the time I say, can you repeat the measurement because the implants have healed and they drift a little bit, abutments move slightly, so let's take a new updated measurement. And most of the time when we compare surgery to healed, there's small movement, right? So if a doctor said, no, I'm not going to retake it, Mrs. Simpson is just a pain, she drives here, she's not going to do it, just go off of the previous photogrammetry, I say I can't warranty the product that I deliver to you for fit unless I have this updated data. So if you as the clinician want to order this, fine, but just understand that if you go to screw it in and it doesn't fit and we have to remake, this is my fee schedule.
Right.
And I do that all the time, right?
You require a second healed implant.
I do. Yeah, I do. I mean, it takes 30 seconds to do when you're doing all the scans. I go back and I tighten all my abutments. I change angulations if I think they're too shallow or deep. I want optimal outcomes, right? This is not chicken shit dentistry. This is life savings dentistry. Susan, or my patient, I'm blanking on her name, Susan, she emptied her life savings for this, right? So I have an obligation as her clinician and then as the lab to deliver a product that I'm confident with. So again, this is just a way to evaluate devices. This is a way to evaluate data sets. So I think it's going to be valuable for us as the lab owners and as the clinicians to have a tool like this.
Have you changed how you use these devices in your day-to-day since looking at this initial data?
Have I changed how I use this? Well, yeah, some of them are getting dusty. All the systems that I used will produce results that can get the patient out the door. There's no bad system. These are all better than analog, and these are all better than intraoral scans. So these are all, like I said, we're at the top of the pyramid already. Now we're just pushing the boundary for tolerance and acceptability a little further for evaluating new devices.
I saw in the video you scanned with the trios.
That was just to get tissue scans.
Okay.
Yeah, I should have done a scan body analysis too, but I don't think that it would go high enough. It would burst through the ceiling and go into the next story. Right. So in my mind, there's analog guppies in the mud, those guys. Then there's the digital but intraoral scanning methodologies, and then there's photogrammetry methodologies. I think that's widely accepted. Now what's happening is the intraoral scanning level is trying to jump and supersede the photogrammetry level. And so when you walk the floor today, you'll see this system and this system, bye-bye photogrammetry, no need, no verifications, and it's based off of intraoral scans that have a deviation of 200 microns.
So when the software comes out, we'll say in a year from now, and you've gathered enough data to where it shows basically people not to get one machine because this one is not nearly as good as the other ones in the market. What are you doing to protect the software or kickback from these scanning manufacturers to come after you?
Again, I'm not going to make any recommendations, and I don't think they are either. What we're going to do is make a public crowdsourced database where people can make their own decisions. If somebody wants to come and say, you know, I'm really pissed that you put that data for pick up there, I'm going to be like, it's just numbers. Please do it yourself. Prove us wrong. Like, provide your own data. Like, to me, I don't think it's going to, if it makes people uncomfortable, okay, right? I'm okay in that space. I know why they wanted to do it.
Well, what I'm saying though is, when a software comes out, especially if there's any charge for it, that company then is responsible for the data they hold. So if a scanner company shows that theirs is the crappiest on the market, they can physically come over and say, hey, I want this removed because basically you're showing that this company's bad and not to go with their stuff. So if it's a free program, that doesn't happen. That doesn't have that effect. It's just available out there for everybody to
Right,
look at.
and that's why this is free.
Awesome.
Free at Lab Day.
So what if you have somebody with an iCam and you're seeing data that's way offline compared to other? Are you going to look at
Great question. Yeah. So if, assuming they didn't move the scan bodies and they followed the protocol, then I'm going to get on the phone and be like, I think maybe you should get that machine checked, get it calibrated, figure out maybe there's something going on because I'm seeing a fail on your cases that I'm not getting from other people.
would a consumer that entered that data would see that result? Would they get that information immediately, or they could assume it pretty quickly?
Well, it depends on who's taking the test, right? So if the clinician is taking the test chairside, which that would be the best, then they're going to see this data right away. They may be like, oh, I don't know, that doesn't make me happy. I'm assuming the lab. On the lab side, if you have a model or you ask the clinician to do this and provide you with the 2 data sets, you can put this into the software yourself and then report back and say, just so you know, look at this data problem versus 100,000 scans on this website. You're way out of whack. Something's not right. What happened? Let's figure this out because I'm going to keep manufacturing full arches for you. I want to make sure that we're delivering the best possible outcome.
Did you, on the iCam, do like 80 views on each one?
I think a manufacturer recommendation is 40,
40?
so
Yeah.
I'm sure we just did that.
Yeah.
Yeah, so pick stops at a certain number, gives you a sound. Micromapper stops at a certain number, gives you a sound. iCam just keeps going, so we probably stopped at the manufacturer
You
recommendation.
40 for?
Yeah.
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 You
Good
did
questions.
A similar way you cleaned off all the scan flags right before, or you just?
Yeah, you can see from the video, it was just my normal protocol. So live surgery, open flap, dry off the scan bodies, take the measurement. And then for the other ones, obviously, we can control a little bit better.
Do you think there's a way to use this data to see which scan flags you need to replace? Like the you know,
Yeah.
like you showed the pic, your
Right.
first one had that one back left one. I was thinking, do you have a photograph to see if that one was more worn or used than the other 3?
Great, yeah, possible, yeah. So if you know which ones you're putting on which sites, because like iCam flags don't have the numbers readily available like PIC flags do, or micromapper flags, they're all uniform. So you'd have to like label them somehow or keep them in order. But yes, potentially, if you were consistently seeing one that was failing, then you'd be like, what's wrong with you, buddy?
Yeah.
Yeah. Yeah, so there's lots of applications. You could use this to see discrepancies between your surgical data and your healed data to see if there's a gigantic discrepancy. You could use any 2 data sets. What I want it to be used for is to evaluate devices and to evaluate reliability of data. so that when claims are made, we can substantiate those claims.
I think with the Micron, you use the original. Have you done any of the split scan bodies yet?
I actually helped with those being developed, so I have them too. I just didn't use them on this because I don't maybe think I had them. They weren't involved in this study, so I can't speak to it. But what she's talking about is Micron Mapper's snap-on scan bodies that sit on a metal base. It would be very easy to do that. You just use those instead of the.
Pay you to do it.
I don't want money for this.
That's what we have.
I'm here friendly.
No.
So yeah, but any scan body, any system that can be used to create repeat data can be tested on this system. So intraoral scans, photogrammetry scans, anything.
What version are they up to now? iMetric ICAMs up to 5?
I didn't understand the question.
The iMetric ICAM.
Right.
What version are they up to? 5?
What version of software or
No, the
hardware?
hardware.
Yeah,
Hardware.
I think it's the 5th generation, right? High five.
Is there your favorite one, or is the newest one the best one?
Newest. I get great results with my Gen 4. I have 2 iCams. So my Gen 4 gives me great data. My Gen 5 gives me great data. Yeah.
Now I'm kind of curious what the difference might be between the generations if you did the same test. Yeah.
That is your homework. Again, what I think is great is this is now going to be available to the public and to you guys because you're all smarter than me. You're going to come up with cool ways to use this. And what I want to see is when we go to this website in 6 months that we are seeing the databases grow across the country and across the world. People are using this to grow this crowdsourced database. And then so imagine a ticker that says 20,000 scans received, 30,000 scans received, and then boom, just all the raw data. Love it.
I just want to say thank you for doing this.
Yeah, absolutely.
I've been wanting to see this for years, and I tried doing it myself, and
Right.
I didn't have the statistics.
Right. Well, you can thank me, but thank them too. Thanks, guys. I consider these guys to be the tip of the arrow and pushing all of us forward to hold ourselves and manufacturers accountable for the claims that they make. And that's what I think the power needs to be, is back with the clinicians. I'm dedicating all of the rest of my career to empowering clinicians and lab technicians and owners to own all of Full Arch. We are slowly giving away Full Arch to corporate entities and to, a lot of different places that want to take all the profit out of Full Arch and leave us with the risk. As lab owners and as clinicians, we need to do everything in our power to control the upside of Full Arch so that it doesn't just get taken away from us. Yeah.
Already have an ICANN, but you need to purchase new one to use the FitMeter.
Do you need to purchase a new iCam to use the FitMeter? No. You should definitely purchase a new iCam though. But no, any device.
Okay.
Any device, any Full Arch implant capture device can be tested on this.
Is this only tested for multi-units purposes, or can you test it going direct to the implant?
Can you test it going direct to implant? Yes, this is just a mathematical tool.
Okay.
So you can test any group of data. This is unbiased mathematical analysis that we need. So anything. Yeah.
Did you use the newest one for that? For your
I believe so. Yeah, I believe so. Okay. Gosh, great questions.